Hello, my name is Pauline Laporte, and in this short presentation, I would like to present you what we have been doing in work package 1 of the MegaAlert project that deals with the wave structure interaction problem. So this presentation is meant as a high-level 101 type introduction, and any equation or figure that are presented in the slides are only here for the beauty of it. But I would also, of course, welcome any question that this presentation may lead to, and you will have my contact details at the end of the presentation. As you may know, the work package focuses on increasing the understanding of the wave structure interaction problem that affects the wave energy converter. And this understanding is critical when considering the design, implementation, and integration of the system. So one of our critical tasks in this work package was to look into the impact of novel control algorithm, in particular considering a wave-by-wave prediction-based method. So looking at the impact on the system's survivability and on its performance as well. So in the first step in this presentation, I would like to give you some brief information regarding the system that we are looking at and what we have developed so far to give you some context. And then I will dive into some details on the study that we have conducted, the approach that we followed, the results that we obtained, and some preliminary conclusions on them. So the MegaAlert project builds on the knowledge gained from previous development of the wave roller wave energy converter developed by AWE. And a range of key innovations are being included in the system, among which is a wave-by-wave control strategy, where force control parameters are adapted on a wave-by-wave basis. And considering the efficiency and reliability are two key challenges for PTOs that need to process large alternating forces in order to extract power. And the focus of MegaAlert project is therefore to design, build, and validate a generic, high-performance, cost-efficient, and reliable PTO that can be integrated into wave energy converters, and therefore then being massively deployed on a global scale. To validate the PTO, a test rig was built in AWE's facility in Finland to test it under a range of load cases and control strategies, and the results of which will also be used to validate the numerical model that we have developed in this work package 1. For your information, AWE has developed and regularly adds a range of pretty nice videos that are focusing on quite interesting news, and they're all posted on their YouTube channel. I would very much like to invite you to check, in particular, that one that is that shows the completed facility. So the development of a wave-by-wave control strategy requires a software algorithm that can predict ocean waves activity in the next 10 to 20 seconds. That's crucial for the innovative PTO that has wave-by-wave control. The software was developed by our partner, the Leibniz Institute, and is at its core a neural network prediction algorithm. There's some news or some blog post on the MegaAlert website from our partner that describes it in a bit more details. But essentially, we feed wave elevation time series into an echo state network that then computes a prediction of the surface elevation associated to the next few incoming waves. And for wave elevation data, we've been using the nearshore wave propagation Busnest model that was developed by our other MegaAlert partner, the University of Bergen. And there's an example of output in the figure here on the left. Based on the output from the prediction software, the MegaAlert PTO settings can be optimized in terms of force characteristics at each of the two drivetrains on a wave-by-wave basis. And that's where we can start looking at the different control strategies of interest. So starting from a baseline strategy with a simple damping force applied, with the force control parameters optimized by C-state, and the same force applied at both drivetrain and a force cap, we can consider the force parameters as the damping coefficient on one end and the force split between the two drivetrains. And two applications of wave-by-wave control, two applications of wave-by-wave prediction tools can be considered. So one aims at maximizing the power capture and optimizes the damping coefficient on a wave-by-wave basis. And another strategy focuses instead on using the control system to increase the survivability of the device by adjusting the force split. This is particularly useful when we consider waves approaching from an oblique heading that generates a hydrodynamic torque load about the bearings that connect the prime mover to the foundation. So we can try to minimize these loads by adjusting the PTO force splits between the two cylinders of the mega-Euler twin drivetrain. And this split adjustment can actually be done on a C-state by C-state basis or on a wave-by-wave basis. And we'll look at both options in this study. So as mentioned earlier, the purpose of the study was to investigate the potential benefits of the wave-by-wave prediction tool in the performance and survivability of the system using a custom numerical model that we developed in WEXIM as part of the project and as part of work package 1. The survivability is defined as the ability of the system to withstand extreme loading events and high fatigue cyclic loading. And in an initial step, we focus only on the fatigue loading and consider normal operating conditions. Extreme loads are considered outside of the scope of this study at the moment. We considered a range of regular and irregular waves, taking as basis the wave conditions at the Peniche site in Portugal that is used as a reference throughout the mega-Euler project. And then as key metrics that we focus on in this study, for performance metric, we estimated the mean annual energy production. And for survivability, we look at the bearing torque and compute the root mean square value of it. This gives an initial approximation of the magnitude of the torque loading, and that's judged acceptable in operating conditions. And a second metric that we look at is the damage equivalent load that gives an accurate measure of the fatigue loading. To investigate the effect of the wave-by-wave damping control on power production, so that aims at maximizing the power capture, we looked at the same C-state using the baseline control strategy and using the wave-by-wave damping control approach. And overall, it was found that the increase in energy production is relatively small when moving from a baseline strategy to a wave-by-wave damping control approach. So this may be due to the mega-Euler characteristics, specifically the fact that the device is not designed to resonate with the waves. And these findings are obviously not meant to be interpreted that wave-by-wave damping control cannot be suitable for other wave energy converters. So that could be investigated in subsequent studies, so looking at other type of devices. And we could also look at more complex control strategies. So, for example, introducing additional terms in the control, looking at adjustable stiffness, for example. But all this complexity needs to be considered as well when we observe potential performance gains. This needs to be weighed against the increasing complexity of the PTO drivetrains. So this is for the control strategy aiming at maximizing the power capture. The other potential application of the wave-by-wave prediction tool is to look at survivability gains. And in this case, we started by looking at regular waves. And as shown in the figure, when we compare the red and the blue lines, that is the total bearing torque, either using a baseline control strategy or a wave-by-wave PTO force split adjustment, then we can see that this wave-by-wave force split controller is able to significantly reduce the total torque on the bearing. When assessing the impact in the case of irregular, more realistic C-states, the force control strategy is shown to reduce the total torque on the bearings even more when applied on a wave-by-wave basis rather than on a C-state-by-C-state basis. So this shows the potential benefits of this control strategy, especially when considering the opportunities to further refine, for example, the hydrodynamic torque prediction. So there's potentially a few further studies that can be conducted, but we can see already a good application of a wave-by-wave prediction tool. In conclusion, the wave-by-wave approach was found to result only in a small increase in energy production on a wave-by-wave basis is not likely to be beneficial when considering only power production. This is possibly due to the characteristic of the megahollow WEC, which is not designed to resonate with the approaching waves. On the contrary, an asymmetrical PTO force split can significantly contribute to the survivability of the system when applied on a wave-by-wave basis. And this may represent a potentially more suitable application of the wave-by-wave prediction tool. This is, of course, very much a preliminary study, and the next step could look at, for example, the refinement of the hydrodynamic torque estimation used in this study, or the optimization of the PTO damping considering survivability criteria, for example, by moving away from the PTO damping coefficient leading to the maximum. We could also look at extending this study to consider extreme loads that are likely to be driven by extreme sea states and or fault scenarios that we haven't looked at the moment in this preliminary study. But then overall, the trade-off between power and loads can definitely be studied further, and this will most likely be the subject of future works. Thank you all for your attention. I hope that this presentation taught you some of what we were doing on the Work Package 1 megahollow project. Feel free to reach out if you have any question or comment on this presentation.